I'm going to spend a little bit of time talking about equilibrium concentrations or calculations, because many students have a particular amount of difficulty with this part of the chapter. And I want to make sure that everyone understands how we go about doing this. Now let's say that we have our reaction here, which is nitrogen plus hydrogen forms ammonia. Now, when you start out in equilibrium, you'll generally, in many cases, start out with some amount of nitrogen and hydrogen on the left side and no ammonia. And so whatever they give you as the starting concentrations, you would write those down. Now these numbers can be anything that the problem gives. The problem could give you 0.5 for the two reactants and 0.25 for the products. It doesn't matter. Just what matters is that you write this down as the start of the reaction. Then you arbitrarily assign X or some letter as the change in concentration for each of these. If that is the change, then after the reaction reaches equilibrium, you'll have 1 minus X, because it's 1 mole is used, or 1 molecule is used in each reaction for the nitrogen, 1 minus 3X for the hydrogen, and 2X for the amount of ammonia that is developed. And so what I want to show you here is that the coefficient, once you say that the change in concentration is X, the coefficient impacts what you end up at the end. And so if we were to consider another reaction, this is acetylene plus bromine forms ethane, 4-bromoethane. So again, if you start out with nothing in the products and the reactant's a certain amount, the change in reaction, in this case, again, notice the effect of the coefficients. Now, if you have an equilibrium constant, you would put these, and you didn't know any of the concentrations, you would put these X's and 2X's in. Obviously, you could calculate, if you started out with nothing on one side and this amount on the other side, you could calculate what you had at the end. So there are 3 types of calculations that you can perform given any particular set of numbers. And so there are 3 types of problems that I can give you. And the slide itself is an example of one of them. The slide itself shows you how you would go about calculating the equilibrium constant. The slide itself shows you how you would go about calculating an equilibrium constant given the numbers that are in this problem. And that's the first type of calculation that you would perform. You have certain concentrations and you calculate an equilibrium constant. And you notice here, what you do is you start out, you have 1 molar hydrogen iodide and no hydrogen and no iodine. Then the change is X and X on the hydrogen and iodine side and 2X on the hydrogen iodide side. And so at the end of the reaction, you have 1 minus 2X for the concentration of hydrogen iodide, and it's given what these X's are. So you can put those in and do the numbers, and it gives you calculate the equilibrium constant. The other types of calculations you can do include a calculation of a missing equilibrium constant, that is concentration, that is you're given an equilibrium constant and some of the concentrations, but one is left out. So for example, let's say that I told you that the equilibrium constant was 0.14 and the concentrations of hydrogen and iodine are 0.214 and 0.214, then you're asked to calculate the equilibrium concentration of hydrogen iodide. Or you could calculate final concentrations from initial concentrations. And so I'm going to do a couple examples of these, and then in class, if you still have questions, we can go through and do some other calculations. Now here's another example. This is a situation where one of our favorite problems, carbon monoxide plus water gives hydrogen plus carbon dioxide. And it says under certain conditions of temperature and pressure, 2 moles of carbon monoxide and 3.2 moles of steam are left to reach equilibrium. At equilibrium, 1.6 moles of hydrogen and 1.6 moles of carbon dioxide are present. Calculate the amounts of carbon monoxide and steam in the equilibrium and the value of the equilibrium constant. And it shows you right here, you have this ice, which is the starting concentrations, the initial, the change, which you added 1.6 on the right to each, so you subtract 1.6 to the left because all the coefficients are the same. So at the end, you have the concentrations that are shown at the bottom, and that gives you the answer to the first part of the question, which is what are the carbon monoxide and steam equilibrium concentrations. Then you put this into a reaction quotient calculation, and it tells you the equilibrium. I'm sorry for the quality of this slide, it's a little blurry, but here's another. Some people use a box to do these calculations. You have a mixture of 0.25 molar water and 0.25 molar carbon monoxide. It's allowed to come to equilibrium. Calculate the equilibrium concentrations of all the chemical species if the equilibrium constant is 4.24. Now, this is the third type of problem I was talking about. You're given the initial concentrations, and you're asked to calculate the final concentrations of all the products. Now the equilibrium constant is shown in the bottom left, and you can see the change here is plus x on the right side and minus x on the left side. So at equilibrium, each concentration is shown, and so you would end up with x squared in the product. So that'd be on the numerator, and 0.25 minus x, that quantity squared on the bottom. And that would equal your 4.24. And when you do this math, you'll see that, and we'll show it in just a second, that you end up with a quadratic equation which requires the use of the quadratic formula to find the answer. So we're going to do a couple problems like this to give you an idea of how this works, where we actually do the calculation to the end. And the first one says calculate the number of moles of hydrogen iodide that are in equilibrium with 0.125 mole of hydrogen and 0.125 mole of iodine in a 5-liter flask. And the equilibrium constant is 50.2. Okay, so there's a few initial steps. First of all, we know that the equilibrium constant is going to equal the product. It's the reaction quotient, so it's the product concentration squared divided by the reactant concentrations. Now in this case, now we said we have 1.25 moles in 5 liters, so that's going to be 0.25 molar, and that's the concentration of hydrogen and the concentration of iodine. Now we start with, and we know that the concentration of, we can say that the concentration of iodine is hydrogen iodide is X. Now the 2 here doesn't because it says we're already at equilibrium. So you don't have to worry about the 2. We're just going to use X as the concentration. So that means that plugging that in here, that X squared divided by 0.25 times 0.25, so 0.25 squared, is going to equal 50.4. So X squared is going to equal 3.1375. That's, you square this and then multiply it by 50.4, so that X is going to be the square root of that, which is 1.77 molar. So that if at equilibrium, the concentration of these is given here, then the concentration of hydrogen iodide has to be 1.77 in order for the equilibrium constant to be 50.4. So that's the first one. Now the second one looks like this. Carbon reacts with water vapor at elevated temperatures to form carbon monoxide and hydrogen. What is the concentration of carbon monoxide in an equilibrium mixture starting with a concentration of water of 0.5? Now first you have to do the equilibrium constant, and the equilibrium constant, which is 0.2, is going to be equal to the products, which is carbon monoxide and hydrogen concentrations. Now carbon is a solid, so it's 1, so you only need the water on the bottom, and that equals 0.200. Now we said that the equation is C plus H2O goes to form CO plus H2. So initially, it doesn't matter what this is initially because it's not in the formula. The water concentration was given as 0.5. That's right here, 0.5. Initially, there's none of this and none of this. The change, we'll say the change in concentration of these two, each is X. The change here is 0.5 minus X, or it's minus X, excuse me. And so the final is going to be 0.5 minus X. And this is X, and this is X. And so these are what you're going to use to find the answer over here. So now 0.2 is going to equal X times X divided by 0.5 minus X. So that means you got 0.1 minus 0.2x is equal to x squared. So 0 equals x squared minus 0.1, or excuse me, plus 0.2x minus 0.1. And if you can plug this into your negative b plus or minus. So x equals negative 0.2 plus or minus the square root of 0.2 squared minus 4 times a, which is 1, times c, which is minus 0.1, all over 2a. And if you do all the math here, x is going to be either minus 0.43166, or it's going to be plus 0.231662, and we know it can't be a negative number, so the answer is x is going to be 0.232 to 3 significant figures. Now, so that tells you that the question is what is the concentration of CO? Well, CO is X, so this is the answer that they're asking for. Now, there's a way of checking this. the way of checking this is to take and put this number in for x, 0.232 times 0.232 divided by 0.5 minus 0.232, and see what answer you get. And you should get 0.2, and if you don't, then you made a mistake. And I've done the check here, and indeed we do get 0.2.